we're going to talk about today is just how we use some of those numbers on the periodic table to find some information about the element. Okay? And so what we are going to do is use the periodic table entry to calculate the number of protons, electrons, and neutrons in one atom of that element. And it's pretty easy, really, once you know how to do it. Okay? So, to find the number of protons, neutrons, and electrons, first, number of protons is just the atomic number. Number of electrons is also the atomic number. Okay? Number of neutrons, you round the atomic mass, and then you subtract the atomic number to get the neutrons. So if we look at oxygen, how many protons does it have? Emily?
8.
8. Megan, how many electrons? 8. How many neutrons? Shane?
8.
How did you figure that out?
You round 15.994 up to 16, subtract by 8, you get 8.
Yes. So round this to 16, subtract the atomic number for 8. Okay, fluorine. Thomas, how many protons?
9.
9. How many electrons, Tanya? 9. Sebastian, how about neutrons?
10.
Yeah, 10. You round this to 19, subtract 9. There are 10 neutrons in fluorine. Gold. What is one property of gold that you may be familiar with?
It's soft.
Okay, it is soft. Something else. Yes, it's very dense. If you look at its periodic table entry now, can you guess why it is so dense? Laura?
No, that's not.
Yes. Why is its atomic mass so high?
Because it's so dense.
Why is its atomic mass very high? Higher than you would think for its atomic number. No, not because of the protons. What's giving that atom most of its mass? Let's do this first. How many protons in gold, Raymond?
7.
What? 79.
I forgot.
Maya, how about electrons? 79. Mian, how about neutrons?
118.
Okay, 118. So why is gold so dense?
Because there's so many neutrons.
Yeah, it has a lot of neutrons. 118 neutrons, giving that nucleus of gold a very high mass. And when you add up all those atoms of gold, it makes for a dense substance. How about helium? Number of protons, Donovan.
2.
2. Electrons. Caitlin.
2.
2. Go on. Neutrons, 2. All right, you guys got this? How to do it?
Yes.
Yeah?
Is this our homework?
Not quite,
Dang it.
but yes, mostly.
Most
Most of your homework is doing what we just did.
So you said it took a long time. It's hard.
It's not, there's just a bunch of problems. It's not hard. All right, so if you think back, why are the atomic masses not whole numbers? If protons have a mass of 1, neutrons have a mass of 1, electrons 0, well, you would think that all the atomic masses would be whole numbers. But they're not, because there are slightly different forms of these elements. So, let's take gold, for example. Okay? There's different types of gold. We call them different isotopes. Do they have different atomic numbers?
Yes. No.
No.
Yes.
No.
Yes.
Oh.
All right, who wants to justify their answer? What are you saying, Donovan?
I say no.
You say no, why?
You said yes 400
All right, well, what is your justification?
Okay, because when you look at the number for gold, the atomic number, it's a whole number. So, like, if you had a decimal, then you would know they were.
Okay.
Yeah.
All right. Other ideas? So I'm telling you, there are different types of gold. They have different masses. Is it because they have different numbers of protons?
No.
Okay, let's say we had a gold atom and had one extra proton. Is it still gold?
No. Yeah. No.
No. The
No.
atomic number
No.
defines it.
What is it?
It's whatever
Whatever
electrons gold. Whatever set. Whatever 80 or 80.
Mercury.
Mercury.
So no, the number of protons in all gold atoms
It's 79.
are always 79.
I was right.
So what can be different then?
Like the atomic mass.
And if the atomic mass is different, it's because they may have different numbers of neutrons. Okay? We call those isotopes. Okay? An isotope is an atom of the same element, but with a different number of neutrons. And just about all elements have various naturally occurring isotopes. If we look, carbon as an example. Okay. There are three main carbon isotopes: carbon-12, carbon-13, and carbon-14. Okay. And so if we look at these diagrams showing the atoms, okay, carbon-12, right, has, so as you know, carbon's atomic number is 6. Its atomic mass listed in the periodic table is 12.011. Okay? Carbon-12 is the most common form of carbon. It has 6 protons, obviously, because it's carbon, and 6 neutrons. It's stable. And the vast majority of carbon that you find on the Earth is carbon-12. But there is some carbon-13. Carbon-13 has 1 extra neutron in the nucleus. And that's also stable. But carbon-14 has 2 extra neutrons in the nucleus. So it has an atomic mass of 14 rather than 12. This is actually an unstable isotope. And an unstable isotope may spontaneously break down, emitting particles, alpha particles or beta particles, which is what radiation is. So carbon-14 is a radioactive isotope that decays over time. Okay? And it's not very common, but there's some of it. So when we look at all of the carbon and sort of estimate how much of each there is and average up the masses, that's where we get those decimals in the atomic mass. So on your periodic table, the atomic mass of carbon is 12.011.
No, it's just 1.
12.0111. So again, that would tell you most of the carbon is carbon-12, but there is some of these heavier isotopes of carbon as well. When we average them out, it's 12.011. In fact, carbon-14 can be used in radioactive dating. Okay? Radioactive dating, it's not the kind of dating you're probably thinking of, but radioactive dating is telling the age of something by looking at the amount of certain radioactive elements that are present in it. Because carbon-14 breaks down at a predictable rate. So if you look at some fossilized, no, probably not fossilized, in archaeology they dug up the remains of a campfire from 20,000 years ago. They can look inside of the charred remains of that wood, look at the amount of carbon-14, because they know how quickly it breaks down, they can estimate how old it is. Okay, that's how radioactive dating works. All right. Let's get a little bit of practice here.
So ready.
All right, you do them. Ready, go.
By myself?
Yeah.
Alright,
No,
symbol.
not you. I mean, silently in your brain,
Oh,
writing down the answers. And then we will audibly announce what we have after I
can
call.
I do it?
After you raise your hand. And if I select.
Done. Potassium.
Question, Raymond? Okay.
Wait, we're not doing the drawing items?
Not yet.
Alright.
It's not a race.
Yes, it is.
You know.
Yeah, you're right, it's not a race.
No, I have two side classes instead of going yesterday.
No.
You're right, it's not a race, it wasn't even close.
You're right, it wasn't a race. It's screwed you guys.
We're done already?
Yeah.
Oh, maybe you guys will finish your homework today. All right.
Yes.
Maybe.
He's
All right.
dying.
Who can give me? All right, so let's do this around the room. No hands. Hands down. All right. Emily, the symbol.
Okay,
K.
okay,
Okay. Caitlin, name?
potassium.
Potassium. Olivia, atomic number?
19.
19. Matthew, atomic mass?
39.1.
39.1. Number of protons, Thomas?
19.
19. Neutron, Shane?
20.
And electrons, Noreen? 19. Got it?
Got it.
Okay, next one.
Bro.
Okay, neon. Symbol. BR. Oh no. Sorry. Down below. Symbol. AL. Name, Chippy. Aluminum. Aluminium for some people. Atomic number, Tanya.
13.
13. Atomic mass, Sebastian.
27.
27. Donovan, number of protons.
Protons, 13.
13. Neutrons, Rowan.
14.
14. Electrons, Laura.
13.
13. Okay, Chris. Symbol.
BR.
BR. Okay. Abby. Name.
Bromine.
Yep, bromine. Atomic number. Megan.
35.
What's up? 35. Atomic mass, Raymond.
79.9.
79.9. Protons, Sierra. 35. Neutrons, Maya. 45. And electrons. Rowan? 35. Question? Question, Alan?
Yeah. What is bromine?
It's just, it's a gas. Don't use it.
Can I like some in a jar?
You maybe could, yeah. Shall we do this? Yeah, let's do this. All right, this is quick.
I want it.
I know you want it. So we will sometimes draw a model of what an atom would look like, and it's very simple. What you do is you first need to know the number of protons, neutrons, and electrons. You draw a circle representing the
Nucleus.
nucleus. Okay? Inside, you write in the number of protons and neutrons. So how many protons in aluminum?
13.
13. How many neutrons?
14.
Okay. And then what are we missing to complete the atom?
The electron.
The electrons. Now, so far we have not talked about the numbers on your periodic table that are in the lower part of the periodic table entry, lower left.
Worrying about those.
Okay? Those are what we call the electron configuration. Because the electrons, there's how many electrons in aluminum?
13.
13. They're not just in like a big cluster or a little ball or just flying randomly. They actually kind of orbit around the nucleus at different levels. There are different levels of these orbits, starting from inside and going the outside. These numbers tell how many electrons are in each level. So in the first orbit, there are 2 electrons. So we draw them opposite each other. The first electron shell can only hold 2 electrons. The next shell can hold up to 8 electrons. And then the last shell in aluminum holds how many?
3.
3.
Electrons. So that is one way to draw an atom.
You have to know how to draw an atom.
Yes. And there's another way we're going to do it as well. Now the most important electrons in any atom are the outermost electrons. They're called valence electrons. Those valence electrons are what determines what aluminum will combine with and what number it's going to combine with them. Okay? They determine how it reacts. Okay, if we do fluorine, same thing. 9 protons, 10 neutrons. Its electron configuration is slightly different. It has a full inner shell with 2 electrons, and then its second shell, okay, has 7. We eventually can take the shortcut of just writing the numbers in. You can draw the dots, it's up to you. And the last one is magnesium. Again, it's 12 protons, 12 neutrons, and its electron configuration is 2 in the first shell, 8 in the second, and 2 in the outermost shell. Just to give you a little preview once we talk about compounds. Atoms are generally stable when they have a full outer shell.
How many could be on the outer shell?
It depends on which energy level it is, but generally it's 8.
That's a full.
That's
Some
a
of
full
these are
outer
stable.
shell. So, magnesium, not that stable. It has these 2 extra electrons. How might it become stable?
Lost them.
Okay, there's 2 things that could happen. You can either get 6 electrons to fill it up, but what's easier, Sebastian?
Just lose them.
Getting rid of those 2 extra. Because if it got rid of those 2 extra, then it'd be at 8. Okay? How about fluorine?
It could either get 1 or
It can-
get rid of 7.
Right.
I
So
would
what's
get 1.
most likely?
Get 1.
Get 1.
How does that happen?
So, look at the electron configuration of look at the electron configuration of sodium.
Where's sodium?
Atomic number 11.
11.
It's 281. What would sodium like to do?
Salt.
What would sodium like to do to be stable?
Only would like the salt.
It has 281. What do you want to do, Chris?
Get rid of 1.
Get rid of 1. What does fluorine want?
To get 1.
So what do you think happens?
They
It takes
combine.
And that's why we end up with compounds like sodium chloride, sodium fluorine.
I
What is
got it.
sodium and fluorine combined to make?
Sodium fluorine, I don't know, fluoride. I don't know.
Oh, fluoride.
So,
Isn't that the stuff on your toothbrush?
fluoride is. So anyway, this is how elements combine with each other. The reason they do that is to become stable. All right, let's finish up here.
Whoa.
This is an alternative way of drawing the electron configuration. It's a little bit simpler. What you do for this is you write the name of the symbol, and then we put dots to indicate electrons. But really, we don't care much about the inner shells. The most important one, like I said, is which one?
Outer.
The outermost shell. So we look at that. Aluminum has 3. So what we do is we start on the top. We put a dot for the first electron. Then we go clockwise. That's aluminum's electron dot configuration. Cool.
Next go.
Fluorine.
That's cool.
Write the symbol.
Yeah.
Go clockwise. And now you can sort of see that it's missing 1.
True.
Magnesium. So that's called an